Hello, my name is Brittany Fink. This is my exam 3 for Meng 4312, and it's for System of Dynamics of Controls. We will start by showing the problem, and this is what we will be discussing today, following throughout the presentation. My assumptions for this problem are listed below. They are that I believe that it is a steady state problem. It's also a third order system mathematically, but it behaves as a second order function. The state will be at equilibrium, and it will also be a frictionless system. These equations are very useful in determining the equations for the problem behaving in a second order. First equation will be the second order transient analysis. The next three equations will determine the DC gain, the zeta, and the natural frequency. We begin by solving for the second order transient analysis, and this is the result we received, shown below. And we'll be using this throughout our PowerPoint today. For part A, this solves for DC gain, zeta, and the natural frequency. The results are highlighted in yellow. For the DC gain, we got 0.2. For zeta, we got 0.22. And for the natural frequency, we got 2.24. For here, we have the equations for the final initial steady state values of the output. For the initial theorem, we got 0, and for the final theorem, we got 0.2. For part B in our step response that we did in MATLAB, we got the rise time, which is 0.804 seconds, our settling time, which is 8.11 seconds, and my maximum percent overshoot was 0.5%, and we had no delay time. For part C, our Bode plot, we have an estimated peak gain of negative 6.7 dB, and we also were able to calculate this and do this through MATLAB. For part D, here we have the closed loop transfer function. As you can see, we have this result highlighted in yellow, and it's at the bottom. We also got this chart from our Chapter 10 Part 3 lecture notes, and this helped us to determine the rise time, overshoot, settling time, and the error, and this just gave us an idea of what we were looking for. For part E, the root locus, we have plotted it here and got two poles, and my poles are at negative 0.5, and then plus or minus 2.19. And for the zeros, we got 0 at the zeros, and there we had no breakaway points. So for part F, here we have the root stability criterion, and this will be continued into part G. We have this highlighted below, and this is just how we went through the steps to get where we are here. For part G, we have been given the max overshoot of 25%, the steady state error of 2%, and by using the feedback control, we will determine the range of K. Starting with the equation below, we will replace the S to solve for the result, and then we get a critical gain of 5. Here we have calculated the critical period by taking the times of two peaks, and we got 2.8. And as you can see in the graph right here, I have it labeled. These are the two peaks we used. For part I, we determine our P-only block, K parameter to meet desired specifications. For KP, we got 2.5. We added in the table per our textbook so we could solve for this, and this will help determine for our next parts as well. And I'll take you through that now. And then for part J here, we solve for two PI control parameters for a PI control block for KP, and we got 2.25, and for KI, we got 0.96. And for part K, we solve for 3 PID control parameters for a PID control block. And here we have KP is 3, TI is 2.14, and TD is 1.75. And thank you for your time.